strain at this point, because partial u over partial x actually a strain at this point is equal to 0, means if a strain is 0 means there is no stress applying, is stress on this point, and it means there is no force that is subjected to this point. So it is actually a free vibration, condition of free vibration. So that's why the strain at this extreme end is also equal to 0. So using these boundary condition, you will substitute that one into this solution, into this equation. Let's call it equation 1. So you substitute this boundary condition and find out the frequency equation, the mode shapes, and the natural frequencies. How? And you will try all of these three cases. So how you can do it? If you remember, uh, we performed the solution. Once we reached at this solution, then we applied the initial boundary conditions for the string, and we substituted this u0t into the u equation, and ult into the also into this u equation, and find out ab. And then once, because this is telling you about the the, the movement of this string, or in the case the beam, so it will help you to find out the frequency, classify the frequency of the system. So you will end up getting the frequency response, the frequency of the system, how you can calculate that one. And then you can substitute that in back into the original equations, and substitute the other initial conditions and find out the other parameters. This is what you have to do by yourself, although we'll try some problems or sample equation problems today, so that you will have an idea what you need to do. So you need to calculate this frequency equation, and based on frequency equation we'll find out the natural frequencies, and obviously the overall mode shape. Once you find this AB, you can substitute back into this equation. That will be your mode shape in that case. So that's all for the longitudinal vibration in the strings. Now we will try some cases. You may find some of the solution in your book as well. So if you get stuck, just skim through. I won't tell you where, so that you should open and try to find out in the chapter. It will help you to go through some other steps on the way. So it will enhance your learning. So now we are going to discuss a special case for uh, finding the natural frequency of such bar and beams if it is carrying a mass attached to it. So let's say you have a beam or the bar that is fixed at one end. Let's say you have a beam and it has a mass attached to it at the end. Obviously that beam has some density, it has some cross-section area, it has some elastic modulus, and the total length of this beam is length L. So now you can substitute this one into our original equation. So since one end of the bar is fixed while other is attached to the mass, so the governing equation for the axial vibration for the bar that we've discussed earlier, and the solution that we have found earlier, so we can use the boundary condition, because u at position 0, t would always be equal to 0. There's no displacement at this point at any time, that is at x equals to 0. There's no displacement. So if you substitute this one into our original equation, you will necessarily find the a constant to be equals to 0, while at the end, so if you substitute, I'll write down the equation for you. So if you substitute that one into the equation that we have calculated earlier, like Here's the equation, this one. So I'll just call it equation 1. It will lead you to a equals to 0. Now the next part would be at the other end, the tensile force in the bar must be equal to the inertial force of the vibrating mass. So equilibrium to be achieved, obviously. So in that case, our equation will be a e partial derivative of u with respect to the position at the extreme edge, the other edge, minus of m partial square u over partial t square, and again at the position LD. So using the equation this 8.51, that's equation 1 what you have. So we can so this equation can be expressed as, sorry, AE omega over c cosine omega L over c, and we have c cosine omega t plus d sine omega t equals to m omega square sine omega L over c into c cosine omega t plus d sine omega t. And if we just simplify that one, so we can cancel out this internal bracket, whatever is in there. So we will have a e omega over c cosine omega L over c equals to m omega square sine omega L over c. And since sine theta upon cosine theta is equal to tangent, so it will become equals to, and you can cancel out few things here, omega minus 1, so it will be a e over c into m and e into sine omega LC divided by cosine omega LC, that will be tangent omega L over c. That's what we have. You can even, if you want to class, use some variable, assign this one equals to alpha, so it will become tangent alpha equals to a e over mass into the c constant. This is how you can quantify the response of a beam that has a mass attached to it. It's one of its end.